Welcome to The Explainer. Today, we're going to do something a little different. We're not just looking at history. We're actually going to reverse engineer the ancient mathematical principles that form the bedrock of pretty much all modern technology. We're deconstructing a logical engine designed over 1,000 years ago. Okay, let's just dive right into it. To even begin to answer that question, we have to stop thinking about ancient math as just a collection of dusty old facts. Instead, let's treat it like a masterclass in systems engineering. You'll see that the same principles of logic, abstraction, and efficiency apply, whether you're building an ancient aqueduct or a modern neural network. You know, every great piece of software, every operating system, it all starts with a solid kernel, that core that handles the most basic, fundamental operations. Well, for mathematics, that kernel is the number system. And the engineering goal here was to design one that was complete, totally consistent, and absolutely bug-free. Think about this from a system design perspective for a second. Before the 7th century, basic arithmetic had a critical bug. Subtraction was a real problem. If you tried to take a larger number from a smaller one, that was an invalid operation. In programming terms, it would literally crash the system, throw up an error. So how was this bug patched? Well, around the year 628, the mathematician Brahmagupta didn't just stumble upon negative numbers, you could say he engineered them. He laid out a formal set of rules for zero and negatives, treating them like first-class citizens in the number system. This created the first truly closed logical system, where an operation like, say, 5 minus 8 doesn't crash. It just returns a predictable valid result, -3. System closure achieved. And here's the crucial point. This was a deliberate design choice. It was architectural. This complete logical framework also included the binary system, which was first described in a text on Poetics, of all places, way back around 300 BCE. Using just two symbols, long and short, or 1 and 0, it laid out the fundamental logic that every single computer uses today. Okay, so once you have a stable kernel, your number system, you can start building higher-level tools on top of it. This is where we see this incredible evolution from concrete numbers to an abstract language for problem solving. Think of it like an ancient but incredibly powerful command line. Before this, solving an equation meant finding one specific answer to one specific problem. But by introducing abstract variables, using letters in even different colors to represent unknown quantities, mathematicians created a high-level language. Brahmagupta used this language to write out the general quadratic formula, a universal algorithm that could solve an infinite class of problems with a single elegant tool. And this is a massive conceptual leap. It's the difference between being a mechanic who can fix one car and an engineer who designs the engine for all cars. This wasn't just about finding X, it was about building a reusable, robust, and universally applicable algorithmic tool. I mean, that is pure engineering right there. All right, now we get to the highest level of abstraction we're going to talk about. A concept so sophisticated that, honestly, the best way to describe it in modern terms as an ancient application programming interface, or API. This is where things get really mind-blowing. This perfectly illustrates the principle of modular design. Brahmagupta created a composition law called Bhavna. Just think of it as a function. The goal was to generate new solutions for a really difficult type of equation. So it takes two known solutions as its input, it applies a very specific composition rule, and then it outputs a brand new third solution that is guaranteed to be valid. An elegant, reusable function that takes valid inputs and reliably produces a valid output, that's the very definition of a well-designed API. This idea of composing existing solutions to generate new ones is so profound that, as a recent field medalist put it just blows your mind. And get this, it remains a central theme in advanced number theory research today, which just shows you how incredibly far ahead of its time this architectural thinking really was. Finally, let's look at the applications. I mean, once you have this powerful logical engine, what do you do with it? Well, you build physics, you build engineering, you start to model the world. So early trigonometry, like the kind the Greeks used, was based on the chord of a circle. It worked, sure, but it was clumsy. Indian mathematicians made a clear engineering choice. They developed a new system based on the half chord, or jaya, which we now know as the sine function. Why? Because it was a superior algorithm. It was more efficient, more elegant, and it scaled way better for complex calculations. It was an optimization that directly laid the groundwork for calculus. This drive for precision led to another incredible leap. Around the year 1400, Madhava developed infinite series, including the first ever exact formula for pi. This wasn't just a better approximation, it was a perfect algorithm. It was a method for calculating pi to any desired level of precision you wanted, which for the first time showed how to handle the concept of infinity with rigorous computational logic. And this rigorous approach to change and motion just kept developing. By the 12th century, the mathematician Bhaskaracharya actually calculated the instantaneous rate of change for the sine function as it moved through its values. What is this? Well, it's one of the earliest known calculations of a derivative, the foundational logic of calculus. This is the essential math behind modern physics, the control systems that fly airplanes, and the predictive models that forecast the weather or the stock market. It's the mathematics of change. So, what you should really take away from all this is that these aren't just a list of historical facts. They are fundamental principles of engineering that were defined and mastered centuries and centuries ago. You've got the systems design of a complete number system, the abstraction of algebra, the optimization of trigonometry, the modular design of composition laws, and the dynamic modeling of calculus. And that brings us right back to our original question. What all this shows us is that the core challenges, logic, efficiency, abstraction, elegant design, that define modern engineering have a very, very long and brilliant history. So the next time you're debugging a program or designing a system, remember you're part of that tradition.